Okay, guys. On Friday, we looked at lesson 9.1, the beginning of it, right? Just kind of a brief review. At the beginning of the lesson on Friday, we looked at explicit formulas, and we looked at how to use them, right? So the nice thing about these explicit formulas is you're given an explicit formula, A of n equals, and something in terms of n. If they want you to find the 100th term, you plug 100 in, you do the math, right? That was the nice thing about explicit formulas. Now, we have not practiced how to write an explicit formula, which is what's on today's agenda, okay? So that was that's what we started with on Friday. Then, we started talking about recursive definitions. With a recursive definition, you had to have two pieces, yes? Do you remember those two pieces? Okay, the beginning value, right? Which means you just had to state, what is that first term? A of 1 equals blank. And then you had to give your formula. When we gave our formula, it was always A of n equals, but what was always in that formula? A of n minus 1. And A of n minus 1 always stands for the previous term. In other words, in this case, on a recursive formula, if I want to find the 100th term, I'm going to end up having to know the 99th term. Thank you. Okay? So, with that in mind, we're going to go on the back side now. And I have 4 examples at the back that we're working on. I have changed some numbers again. Okay? So, with an explicit formula, okay, there's not 2 parts anymore. There's just 1 part. There's just your formula. And remember, with an explicit formula, I can easily say, hey, find the 1,000,000th term. Because then all you have to do is plug in 1,000,000 and in for the n value, and you're good to go. So, in this case here, I made that first sequence, 1, 4, 9, 16, so on and so forth. And officially, we're being asked to find the 100th term. Now, if you have lots of time on your hands, you could look for a pattern and keep working your way up, yes? More power to you. Okay? The hint over here, and what I want to encourage, because we need to talk about how to do this, is to write an explicit formula. When we are thinking explicit formula, one of the things I always suggest you do first is think about term numbers. As in, 1 right here is the first term, yes? What is 4 then? It is the second term. 9 is the third term, and 16 is the fourth term. Agreed? Those are your n values. Okay, so when we talk about n represents the term number. So when I ask you to find the 100th term, I need a formula that I can plug 100 in, and it will accurately find the 100th term. So the reason I'm always starting then with, okay, let's write down, I always do it like right above it or something. This is first term, second term, third term, fourth term. You're looking for a connection between those term numbers and the terms in the sequence. Am I making sense here? Now, to me, this one might have a little bit more obvious connection than some of the ones we do. Are you seeing the connection? How does 1 connect with 1? In the same way that 2 connects with 4, that 3 connects with 9, and 4 connects with 16. Can we see the squares here? The fact that 1 is also 1 squared, correct? 4 is also 2 squared. 9 is also 3 squared. 16 is also 4 squared. And obviously we could keep going on and on and on, yes? So, explicit formula. Whoops, explicit formula. And we're practicing this because you have explicit formulas in homework to write or to pick from multiple choice list, 1 to 2. But that says explicit formula, I promise. An explicit formula always begins, just like a recursive formula does, is that it begins with A of n. Because you're trying to find the nth term, whatever term number we want. Now, in this case, what were we doing here? Every time we were taking the term number, 1, 2, 3, 4, and we were squaring it. So what is our formula? A of n equals n squared. Do I have to do anything else with that n squared? No. So this is that if you were asked to write the explicit formula, it'd be A of n equals n squared. You don't need to use the A of n minus 1. And in fact, when you see an A of n minus 1 in a formula, know that it's a recursive formula. Okay, an explicit formula will just use n and something. It won't use the A of n minus 1. Okay, so the whole point of this was to find the 100th term. So if I'm finding the 100th term, what do I do? 100 squared. What is 100 squared? My brain says a 1 with 4 zeros, which is 10,000. Now, the explicit formula made it pretty easy there, right? Huh? You wanted to count them? Well, and we did something similar. We talked about something similar to this on Friday in this class, I think, that, you know, we could say, okay, you're adding 3, you're adding 5, you're adding 7. The next one you're going to add 9, add 11, add 13. You want to do that all the way up to the 100th term? I personally will pass. Okay. Okay, let's try a couple more. Let's look at B. And again, I tried to pick things that I think will help you in homework the most. Okay? That's why you've got so many scribbles and rewrites here. So, annoying, but they should be helpful for homework, I hope. Okay. B specifically says, what is the explicit formula? My sequence is 1, 3, 9, 27, so on and so forth. Now, if I had to ask before we start looking at this, you guys can probably tell me the recursive formula. What do you see happening just as you look at this? 3, and you're always multiplying the previous term by 3, yes? So it'd be real easy to write our recursive formula because it'd be 3 times that previous term, A of n minus 1. However, I didn't ask for recursive. I asked for explicit. So, like last time. So here's what has to happen, folks. We have to find a way to write a formula that when I plug in, say, 4 into that formula, it gives me 27 out. When I plug in 3 to that same formula, it gives me 9. When I plug in 2, it gives me 3. And when I plug in 1, it gives me 1. Okay. The obvious part you guys saw is that we're multiplying by 3. But as I said, that doesn't help recursively. If we take off the 1, don't worry about the 1 for a moment. 3, 9, 27. Do those numbers mean anything to you other than you multiply by 3 to get the next one? Nah, don't go fancy. do you know about, trying to figure out a good way to lead you guys here, 9 in relation to 3? It's 3 squared. Okay. What do you know about 27 in that same manner? Is it 3 cubed? Are you seeing where I'm going with this? 27 is 3 times 3 times 3. Okay, work with me here. 27 is 3 to the third. 9 is 3 to the second. What can I say about 3? 3 to the first? What could I say about 1? 3 to the 0, because anything raised to the power of 0 is always 1. Okay, guys. So, when we write our explicit formula, I want to be able, this is sending us in the right path. I want to be able to write A of n equals, and when I plug n in, it's going to do this. So, when I plug 1 in, I can somehow get 3 to the 0 out of it. When I plug in 2, I get 3 to the first. When I plug in 3, I get 3 to the second. When I plug in 4, I get 3 to the third. Are you seeing something? Starting to see a couple of hands here. What are you seeing, Ethan?
So would it be 3 and then like n minus 1?
That would be the option I would go for. Everyone sees the base of 3, yes? What do you notice about these powers? They are always 1 less than the actual number, aren't they? And so if I say n minus 1, okay, try this out. Does it work? Okay, if I'm going to find the fourth number says I put in 4, correct? And the idea would be that if I put in 4, it's going to be A of 4 equals 3. Whoops. Trying to write this in just in pencil to kind of show you, to test it. But the idea is, if I put in 4, if I'm trying to find the fourth term, A of 4 is 3 to the 4 minus 1. Well, what do you know about 4 minus 1? It's 3 to the third. And what do we know about 3 to the third? It's 27. Did it get me there? Would it get all of my other terms there? Okay, and it should. So you always can test it, which is helpful too. So that's a trickier one, isn't it? But those are some of my hints to look for connections there. The answer, of course, that I was looking for was A of n equals 3 to the power n minus 1. Yes, Carter?
Does there always have to be like a power? Because like I'm just like, I know that probably won't be our numbers. But, like,
Hold that thought, and the answer is no.
Okay.
Abby? Are you talking about like on Friday how we had the n minus 1 being the subscript? Well, on Friday when we did those recursives, that n minus 1, sorry, trying to get it where you guys can see it, that n minus 1 was our subscript, and we always had it on the A. And that was always representing the previous term there. Okay, so that, with recursive, we're using that previous term, and so that A of n minus 1 represents the term that comes before A of n. So if you're trying to find the 100th term, you take the 99th term and subtract 3. Whereas what we're doing today, the idea is if I ask you for the 100th term, you can just plug 100 into the formula and you don't have to know that 99th term. Does that help a little bit? Okay. Good question. Okay, before we go down to C, or maybe I should do C and then my side example. You want to do C?
That's for us.
Yeah. I don't know what bet. I guess. Okay. Sorry, I am all over the place, guys. Excuse me. We'll go ahead and do C because it kind of follows along with the last couple of ones we've done in a way. Okay, so C. What is the explicit formula? For 1, negative 1, 1, negative 1, 1. You know where it goes from there. Negative 1, 1, negative 1, 1, negative 1. So on and so forth all day long. Okay. You guys can probably already tell me the recursive formula. As long as we know the previous term, what are we doing? Multiplying by negative 1. Because 1 times 1 is always 1. And we talked on Friday, I think, that when the sign is alternating, you're probably multiplying by a negative. Now, that's the recursive. Okay? We're not talking recursive right now. So we need to talk explicit. Okay? Did I get your question in there? Okay. Okay, so remember, like I've done with the last two problems, in order to start thinking about term number for an explicit, let's think about, okay, what's the first term, the second term, so on and so forth. So if we think about this is the 1 is the first term, right? Negative 1 is the second. 1 is the third. Negative 1 is the fourth. 1 is the fifth. Those are the term numbers there. Okay? We can't think just multiply by negative 1. Just like on the last one. We couldn't think multiply by 3, could we? We had to change our thinking. You got a thought, Carter?
I think so.
Okay.
But I don't know if we can do this. So could we take it to like the 0 power and then times it by negative 1, multiply by negative 1? Or wait, never mind, because then I would only do this negative. Never mind.
Okay. I know, I'm trying to just process,
Yeah.
If I connect like last time. Last time, you guys said, oh, we're just multiplying by 3. I said, that's great for recursive, but explicit, what did we end up doing? 3 to some power, yes? Okay, there's my hint to you. This time, you guys just told me, oh yeah, I can multiply by negative 1 all day long. But again, how do you find the 100th term if we don't want to find all 99 terms before it, right? That's the type of formula I want. What? Nope. Nope. This pattern will always keep repeating. 1, negative 1, so on and so forth. Because it never ends. Officially, these patterns never end. They keep going on and on. Okay, so, are you catching the hint that here we were multiplying by 3, we ended up doing 3 to some power? What am I suggesting here? Not 1, but negative 1 to some power. So think about this. Could I do negative 1 to the power of n? Does that work? Negative 1 to the first. Does that give me 1? No. Negative 1 to the second. Does that give me negative 1? Negative 1 to the positive second. No, because that would give you positive 1, wouldn't it? Okay, thoughts? How do I change this up? How do I change this up and make this work? Because if I just put it in as is, negative 1 to the n, I'm always going to get the opposite of what I need. Are you catching that? Okay, I'm always going to get not what I need, the other number. What did you suggest? Okay, let's try it. Does this work? Okay. Try it for all of these numbers here. That's our proof. So Eli suggested n minus 1. So if I put in the pink term number 1, 1 minus 1 is 0. What is negative 1? What is anything raised to 0? 1. Okay, put in 2. 2 minus 1 is 1. What's negative 1 to the first? negative 1. Put in 3. 3 minus 1. 2. What is negative 1 raised to n 2, or to an even number? No, negative 1 raised to an even. Negative 1 times negative 1 is going to be positive 1. Is this still working? What if I put in 4? 4 minus 1 is 3. What happens when I take negative 1 raised to an odd power like 3? Negative 1. What if I put in 5? 5 minus 1 is 4. What happens when I take negative 1 to an even power? I get positive 1. Did it work? Yes, it does. Did everyone have that same answer? Because there are a couple other hands up there. You guys all were thinking the exact same thing? And my hint is, I'm trying to say, is there just one correct answer on this particular one? What were you going to try, Kendra?
Brings it to negative n or 1 over.
I'm having to think and process. It's not what I have written down here. So you said, so negative 1 is your base, right? Raised to the negative n. I don't think that's quite going to do it, because a negative n power is just going to, a negative exponent means we have to take it to the denominator, and we still have the same positive or negative sign. Does that make sense? And that's why I'm not thinking, again, I'm thinking on the fly here. But so like if we said negative 1 to the negative n power, I don't think that would quite work. Let me try. So if n is 5, negative 1 to the negative 5th. Negative exponent, remember we take it, to the denominator. So it's 1 over negative 1 to the 5th. 1 over negative 1. Yeah, I'm still going to have negative 1 there when I need a positive 1. So, good. But, I want to think that.
To the 4?
Huh?
To the negative 4?
Nope.
I have it most of the way until the very end. So, hey, real quick, look for Elijah. Could I just have him for a quick second?
Uh-huh.
He'll get right back in to talk more about negative n exponents or whatever that is.
Okay.
They look happy. They look excited.
They are.
Hey, Elijah, real quick.
Okay. Eli had given us n minus 1. What's the variation on that? Instead of n minus 1? What happens if you do n plus 1? Okay. Because here's the deal.
It does the same thing like that.
Okay. And here's what you have to think about, right? In order to take a negative 1 and get it to stay negative 1, we need an odd power, right? In order to get a negative 1 and get it to become a positive, we need an even power. So by either adding or subtracting 1, you're either always going to the next highest or next lowest power. And so you're always changing your even or odd status. Does that make sense? Okay. And this is a tough one to think about. But I still want you to think it through. I have one other option here. I don't know if I dare give it to you or just leave it as is. Yeah, I'll give it to you. I don't know if you guys will like this one or not, but think through this one with me. Obviously, Math Excel would not necessarily be flexible with answers, and theirs is usually multiple choice anyways. But I would be flexible in something like this. So a third option here. Okay. We talked about if you just do negative 1 to the n, it gives you the opposite sign of what you need, yes? So what if I put a negative out here? This is saying the opposite of negative 1 to the n. And you always have to do your exponent before you can deal with that negative. So if you always do your exponent first, you get the opposite of what you need, and then multiplying by a negative basically is what you're doing. Okay? I know, probably not your favorite example today, but I'm trying to stretch your brains here. Okay. One other example I need to throw in. Again, I want an explicit formula. Like all of the ones today, this would be super easy to write a recursive formula, yes? Okay, we're going to think about it, but we're not going to use it because that recursive is going to help me. Okay, so first of all, term numbers. Can you number them so we know what's what? 5 is the first term. 8 is the second term. 11 is the third term. 14 is the fourth term, correct? Those are the term numbers. Now, this is a situation where I think thinking about your recursive formula actually helps you also. Recursively, what are you always doing to the next number? Say it. Adding 3, yes? Well, that adding 3, if you're always adding 3, that's what we're going to multiply in by. Okay, that's how a recursive formula can help you here. And this is, this works when you're always adding the same number. Now, like that one earlier where you was add 3, add 5, it doesn't work that nicely. But if you're always adding the same number, this will work in that A of n is going to be 3n. Then you have to finish off that formula. It's not just 3n. So that 3 came from the fact that we're adding 3 every time. What finishes off that formula? What do you think, Jacob? 3n plus 2. Does a plus 2 make sense if I throw a plus 2 on there?
Yeah.
Will it make them all work? 3 times 1 plus 2 gives me 5. 3 times 2, 6 plus 2 gives me 8. 3 times 3 plus 2 is 11. 3 times 4 plus 2 is 14. So there's my hint on that type of problem. When you're adding the same number every time, it is not coincidental that this plus 3 matches with the times 3. Okay? And then it's just a matter of figuring out that plus 2. And it's real easy to say, okay, if it's 3 times 1 is 3, and I'm supposed to have 5, then I have to add 2. And it should work every time. Okay? Okay, I looked at the word problems compared to types of problems you have in the homework, and I'm not going to worry about these word problems today. They are not going to be helpful to you. So I'm going to say get moving on to homework. Lesson 9.1 in Math Excel.